Today, I am going to introduce the study on serviceability assessment of existing gas pipelines of Ukraine and the hydrogen transportation. The research was carried out under the project implementation supported by the National Research Foundation of Ukraine. Just a moment. What I can. Oh, thank you. As we know, the decarbonized of energy career, hydrogen is already widely used in global energy transitions. And in May 2022, the European Commission presented a plan to rapidly reduce the consumption of oil and gas and fast forward the green transitions. However, the development of hydrogen energy and widespread usage of hydrogen faces some challenges, including its impact on the mechanical behavior of materials used for hydrogen transportation. The main issues is connected with its impact on the mechanical properties of materials used for hydrogen transportation. And as we know, a construction of new dedicated hydrogen pipelines will be complemented with using of existing gas infrastructures. And according to the European hydrogen backbone, 70% could be repurposed by 2030. Ukraine is one of the priority partner in this initiative due to its potential for green hydrogen production, and also due to existing infrastructure connected to the European countries. So there is a greatest prospect for using the Ukrainian gas transit pipelines for hydrogen transportation. However, such a prospect can increase the risk of the structural integrity loss, and as the main issues are in service degradation of long-term operational pipeline stills, and also a potentially harmful influence of hydrogen on mechanical and corrosion properties. Since significant part of pipelines is near the end of their design life, and in-service degradation implies embrittlement and deterioration of mechanical properties. So based on our previous results, two main stages of in-service degradation of pipeline stills were distinguished: deformation, aging, and also in bulk material damages accumulation. And also it was demonstrated that hydrogen plays an important role in accelerated degradation on both stages. On this slide, we can see how hydrogen is involved in damages and degradation of pipeline stills under operation. A pipe can be hydrogenated from inside and outside the pipe due to electrochemical corrosion. And what's more, under hydrogen transportation, it can be also evolved due to molecular hydrogen dissociation, especially on the fresh surfaces formed under deformation, for example, under cyclic loading. So a long-term mutual action of corrosion, hydrogen charging, and the mechanical working stresses facilitates development of the damages at the nano and micro scales, and accelerates degradation. Therefore, it's important to know the current technical state of stills on certain branches of pipelines, and also to assess the sensitivity of operated stills to the hydrogen action. So the aim of the study was to assess the stability of low carbon pipeline still of natural gas pipeline to internal hydrogen embrittlement, taking into account long-term operation and the intensity of hydrogen charging. So a material under study was a low carbon pipeline still with X52 strength grade from two pipes after 38 years of operation on a gas transit pipeline in Ukraine, and for comparison, a reserve pipe unoperated from the same grade steel. Both pipes have the same diameter and a wall thickness. So specimens cut out from these pipes longitudinally and transversely were subjected to characterization, hydrogen charging, testing, and analysis. Analyzing the microstructures of these steels, you can see that they are similar bands of pearlite and ferrite, and also a significant number of non-metallic inclusions oriented in the rolling direction. Here we can see stress strain curves for the studied steels, and also basic mechanical properties for the studied steels. And we can see that there is no significant difference in the strength properties. However, there are some differences in the plasticity characteristics. An anisotropy of mechanical properties for all pipeline steels is a well-known phenomenon, and it's important to know whether long-term operation influences on the anisotropy of mechanical behavior. And based on the presented data, we can see that an anisotropy of basic mechanical properties is insignificant for the studied steels, and also the high strength in transverse direction compared with the rolling one is commonly observed for all steels. And in this case, we have a similar mechanical behavior, except for the operated steels, the ultimate strength is the same in both directions. The plasticity characteristics for the operated steel is somewhat lower than for the delivered one, indicating operational changes in the material. A main feature of operational degradation of pipeline steels is a decrease in brittle fracture resistance. And we can see that impact strength and fracture toughness are significantly lower for the operated steel than for the as-delivered one, indicating in-service degradation of material. I'd like also to note that a detailed analysis on fracture toughness will be presented today by Professor Nikiforchin in other session for these steels. And analyzing impact strength, we can see that anisotropy of this property is significant. So its value for the transverse specimens is almost twice lower than for the longitudinal ones. Therefore, we can conclude that brittle fracture resistance is more sensitive than plasticity characteristic for the assessment of operational changes of the material, and also the anisotropy of mechanical properties. Analyzing fracture surfaces for the operated steel specimens after Charpy testing, we can see surface texture depending on the specimen orientation relative to the pipe axis, and it's mainly associated with delaminations more pronounced for the transverse specimen. And also we can see that width of delaminations characterizing residual opening of the defect under fracture is smaller for the transverse specimen, indicating a lower brittle fracture resistance. To study hydrogen influence on steel microstructure degradation, specimens were subjected to electrochemical hydrogen charging under different modes, moderate and intensive, using different cathodic current densities, which differs in 20 times. And also duration of cathodic polarization was 120 hours, high enough in order to ensure a more uniform distribution of hydrogen in a cross-section of specimens. So analyzing microstructure after hydrogen charging, we can see a cracking of non-metallic inclusions for the operated steel, and also all non-metallic inclusions have at least a partial loss of cohesion with the matrix. And after intensive mode of hydrogen charging, also cracking along the boundaries between non-metallic inclusions and the matrix was observed, and complete decohesion of non-metallic inclusions from the matrix formed defects in the steel. On this slide, we can see stress strain curves for the delivered post-operated and hydrogen-free charged specimens. And we can see that there is no remarkable difference in strength properties for the studied experimental conditions, as well as steel state and orientation of specimens relative to the rolling direction. And plasticity for hydrogen pre-charged specimens is decreased, especially for the operated metal. Here we can see how hydrogen influences on a reduction in area for the study stills, and the lowest values were observed for the operated metal. And hydrogen embrittlement susceptibility for these stills was estimated by changes in reduction in area due to preliminary hydrogen charging. And as we can see from this data, as delivered steel is not sensitive to hydrogen embrittlement under moderate mode of hydrogen charging, and it's somewhat sensitive to it under intensive mode of hydrogen charging for the transfer specimens. And for the operated steel, we can see that it is sensitive to hydrogen embrittlement for under both mode of hydrogen charging, especially for the transfer specimens. And also it should be noted that under intensive mode of hydrogen charging, the susceptibility of the operated metal to hydrogen embrittlement is very high. So analyzing fracture surfaces of the specimens for non-hydrogenated and hydrogen pre-charged specimens, we can see that the fracture mechanism for non-hydrogenated specimens was ductile, and for the operated steels also delaminations were observed. And after hydrogen charging, delaminations oriented in the rolling directions were also observed for the as-delivered steel, and also a complete decohesion of non-metallic inclusions were observed for both study steels after intensive mode of hydrogen charging. Additionally, for the operated steel, near the lateral surfaces of the specimens were observed intergranular embrittlement, and while for the operated steel also after intensive mode of hydrogen charging, brittle transgranular cleavage. So these distinctions were associated with different ways of hydrogen diffusion in the steel, depending on intensity of hydrogen charging. So here's some concluding remarks. I will not repeat them. And I'd like to also emphasize that further research will be focused on the study of hydrogen action on fracture toughness of these steels, especially for the operated metal, and also on development and validation of new criteria for assessing a critical metal state in order to ensure serviceability of the operated pipeline steels for hydrogen transportation. And also these findings, this project is focused on the Ukrainian gas pipeline. However, these findings can be also extended to other pipelines sharing similar operational conditions and safety requirements. Thank you for your attention.